This video is going to prove these three bullets about hedging with actual volatility. And what we mean by hedging with actual volatility is we use the actual volatility number to calculate the delta to figure out how many shares we short, as opposed to using the implied volatility to calculate the delta to figure out how many shares we short. So in this video, we're hedging with hedging with actual volatility. So the first thing is we know at the end, in theory then, how much money we will net. The difference between the value of the option using actual volatility and the value of the option using implied volatility. That's how much money we should make. The second bullet, which we'll show, is that we don't know the path that net money takes from its initial value of 0 when we first set up the hedge to the final value of the place that we know it's going to end, the value of the call option at actual minus the value at implied. And because we don't know the path, that path might have some negative steps in it. We might lose money one day. But that's okay. We know how much money we're going to make in the end. All right, let's start with our hedge then. Our portfolio that we set up is we are buying the option. So throughout this video, I'm making the assumption that the actual volatility is larger than the implied volatility. So we want to buy the option. If it's the other way around, then we're shorting the portfolio rather than buying the portfolio. But the math will be the same. So let's proceed ahead then, assuming that the actual volatility is bigger than the implied volatility. And of course, that's why this difference is positive. So first thing we do is we short some stock. How much stock? Well, we need to calculate the delta. We're using the actual volatility to calculate the delta. So that's delta superscript A for actual. We short that many shares. Some money comes in. We take some of that money and we buy one of the options. Of course, we're buying it in the market, and the market is using the implied volatility. So this is how much the option costs using the implied volatility. We take this money and we invest it at the risk-free rate of return. We take this much money that we get from shorting the stock, and a little bit less because we bought the option, but that's our portfolio. So we take that and invest it at the risk-free rate of return for a time step. So what happens in the change in our value? Well, this money minus the cash so that's how much money times that dt. Okay, this piece, that's the amount of money, our cash that we invest at the risk-free rate of return for a time step of dt. That's the change in our cash. The change in our portfolio then would be represented by its derivative, the change in the value of the option. Now the option is going to change because of two reasons. The stock could change, and time will certainly change going on the dt. And our ds, we're making the assumption here that our ds is a log normal. So ds is that mu s dt plus sigma s dx, where dx is that normal random variable. Anyway, this is what we've got here is our change in our net. That's our tiny little change in money. Now if I repeat this line, so this is our like little net change, or I'm going to call it d net, the change in the net. If I take this line and I change this to an A, and I change this to an A, what does that mean? Well, this is setting up a balanced portfolio, but I'm using the same volatility for calculating everything. I'm using the actual volatility in this case. So the change is supposed to be zero, because if we set this up in this manner, we're supposed to eliminate risk. It should be a risk-free investment. So the change in our portfolio should directly equal the change in our cash. So these are two true equations. What I'm going to do then is I'm going to take the top equation minus the bottom equation. So that's going to be top equation minus the bottom equation. So that'll be dVDI and subtract this one. Now these two pieces with the ds, they'll cancel out. Also, this R delta AS and R delta AS, that also cancels out. So from this bracket minus this bracket, we've got our R, and that's only going to be our VI minus VA dt. And that'll be d net, the change in the net, minus 0. So now let's approach this from a slightly different angle. Consider this expression, e to the RT times the derivative with respect to time of this expression. Well, let's take our derivative. I'm going to have to do product rule here. I need to take the derivative of the first with respect to time, which would be minus R times this. So I'm just looking at this derivative here. That would be minus R, leave the second alone, plus leave the e to the minus RT alone, taking the derivative of this bracket, which will just be the d's in front here. And, I've also got this multiplied by e to the positive RT. So that's going to cancel that out, and that's going to cancel that out. And this is exactly this. So in other words, this change in my net money, I can think of the change in my net money as equal to that expression. So that's the little change in my net money over one time step. So what do I want to do? Well, that's how much money I make over a little time step. I want to add up all of the, the amount of money that I make over each time step. So I want to sum all these little changes up over time. So the total net, or total profit, however you want to say it, is going to be then the integral of all these little d nets, which we already said is this. And I'm starting at the time it is now, and I'll just call that t naught, and I'm going to expiry time, t, and I've taken that e to the r t naught outside. So now I'm integrating this derivative with respect to time. So that's going to be equal to still got my e to the minus RT naught here, times this expression with the time, subbing the top minus subbing the bottom. So I'm subbing in this capital T expiry time minus this whole thing subbed in with the bottom, T naught, the initial time. Now, when I sub in capital T here, here's the thing, that at expiry, the value of the option is given by its payoff. doesn't matter. There is no place to plug in a volatility. So at expiry, V sub I is equal to V sub A. So when I sub in the time here, this whole piece is 0. When I sub in T naught here, I get the value of the option using implied at T naught minus the value of the option using actual at T naught. This will be minus R T naught. So this e to the positive R T naught and e to the minus R T naught cancel out. This minus can go inside and flip that VI minus VA around, and I get notification. And I get this, the thing that, so the first bullet has been proven. That sum up all the little net that I make from each time I rebalance, and I get the value of the option using actual minus the value of the option using implied. First bullet's done. Now to show the second bullet, that I don't know what path I take from 0 for the net, that the net takes from 0 to this known value. All right, well, so I'm going to take one of the changes, one of the little changes. I mean, we summed up all the changes, but I want to see what happens to just one of the little changes here, the change in the net. I already know what the total sum of them is. And let's investigate that. I've got a couple of facts here. Here's the, using Ito's lemma, I've expanded using Ito's lemma the value of the option at implied. So that would be equal to its derivative with respect to time, dt, its derivative with respect to stock, ds, plus its second derivative with respect to stock, ds squared. But the ds that we're using, of course, because we're thinking about log normal, that's going to be equal to mu. It's hard to find mu. Mu s dt plus sigma s dx. But what sigma am I using? That's the actual sigma, right? The stock that the stock is moving at. So when I take the ds squared, I'm going to get some dt squared, too small. I'm going to get some dt dx's, too small. The only thing that survives is that dx squared, which quadratic variation is a dt, and so that's why I've got the sigma actual squared s squared dt times the gamma. The gamma is the second derivative with respect to stock. Also, I've got Black-Scholes here, and Black-Scholes is true as long as I use the same volatility in all the expressions. So here I've written it out using the implied volatility. All right, let's get back to our little change in net here. I can use Black-Scholes to replace this piece here. So instead of dv, no, not Black-Scholes, sorry, Ito's lemma, I'm going to use this piece here. Undo. I'm replacing that dv. I've still got all of these things here. And that still equals d net. Now, let's use this Black-Scholes to replace this piece. But here I've got a minus r dt. I'm going to multiply that through the bracket. So that'll be, and that'll make this a plus r with the dt. So I'm just expanding that bracket because then I've got this piece here, which I can replace with this expression from Black-Scholes, that RV. and each one of these will have a dt in it. Let's multiply this. If I multiply this dt through the bracket, that's going to put a dt here, a dt here, a dt here. All right, this thing's just getting bigger and bigger, but it's going to simplify in a second. Here I've got theta I dt minus theta I dt, so these cancel. That's a nice thing. And I've got these gamma sub i's that I can group together. So I'm going to take this bracket off, distribute the minus sign through, and then group these pieces together. Because this piece here, I can do some factoring. I can take out an s squared out of both, I can take a half out of both, I can take a gamma. I can take everything except for I can factor that out of both pieces. And now I've just got these differences in the sigmas squared. Can we do some more like clever factoring stuff here? Well, I can see here that I can factor out some of the deltas. Let's think about then what well, we got ds here, ds here. Let's group some more stuff. So here I got some with the r's and the deltas. I'm going to put this here. So now I'm going to factor across this bracket here. I just moved it around so I don't have to worry about taking a minus sign. I can take an r to the outside. I can take an s dt to the outside. And here's just a difference of the deltas. If I look at these pieces too, I can do the same thing. I can take out a ds, and now there's just this difference in the deltas. Now I'm going to take a minus sign out so it's the same order. Now across this, I can factor out that bracket. Okay. Now let's think about putting in this ds, I guess, because we know what ds is. And distribute that minus sign through the bracket. Minus. Let's put this piece here, and then across this, I can take out an SDT. I'm just trying to simplify this. And what am I seeing here? Well, I see that usually the drift is bigger than, so I know I switched these around, but I think it's going to be nice to take out a minus sign from this whole square bracket, make this a plus, switch these, and then switch these back. Sorry, I switched it and I switched it back. But anyway, I've got something that I can work with. Remember, we're assuming that the actual volatility is bigger than the implied volatility. So this expression is positive. Positive. I guess the real point is, oh, and this is positive. Positive. The real point is right here. The little change still has a dx in it. There's still a random component for this little change. So that's our proof of the first, we don't know the path that the neck takes from 0 to the difference in the value of the options because of this randomness. And it also depends on what the stock is too. So each little change is dependent on the stock value at that current time, plus that little randomness. So what was the point of all this? Oh, and some days we might lose money. Let's go to the back of the change too, because we wanted to show that. That'll be if the change is negative. Well, this is positive, but this dx, that could be a positive or a negative number. The difference in the deltas, well, let's concentrate on this fact here then. The dx could be a positive or a negative number, so this piece could be positive or could be negative. So it's conceivable that the change in the net value could be negative if I'm hedging with actual volatility. So we've proven our 3 points then. If you hedge with actual volatility, I know how much money I'm going to make. It's just the difference between the value of the option at actual volatility and the value of the option using implied volatility. But we don't know how we're going to get from our net money is going to get from 0 at the beginning when we set up the hedge to that known value at the end. And because we don't know that path, we also showed that some of the days we could lose money.